Does anybody have any questions you'd like me to go over? Certainly. 15 and 14 are the two tough problems. Let's start with 15. When that polynomial, which has two parameters that are missing, a and b, is divided by x minus 2, we get a remainder of negative 5. And when we divide it by x plus 1, we get a remainder of negative 16. So Miles and I were working this morning on question 14, and I said to Miles, well, I'll probably do 14 in more detail, but I won't, because 14 is the same kind of thing as 15. The bottom line here is that this statement tells us that when we have this polynomial function of x, it tells us that when we put 2 in for x, what comes out is negative 5. So I'm choosing to explain this a different way than I did this morning if you were in Sabre support. On the other hand, this statement is telling us that when we put in x equals negative 1 into the equation, what pops out is negative 16. So I got a lot going on here. I better color code things. Right? And then when I put negative 1 in, what comes out is that. I mean, I could make a table, right? I could say x remainder or a remainder. But the bottom line is when I put 2 into this equation, I'm going to get 3 times 2 cubed plus a times 2 squared plus b times 2 minus 9. And this has to give me negative 5. And looking at your expression here, you doing this, but it's not working out. Okay. That's one equation that relates the two missing parameters, and we're going to need a second one because there's two unknowns. You learn this kind of in Math 10 at the end of the course, that a single equation can be solved for a single unknown, but if you have two equations, if you have two unknowns rather, you need two equations. You don't go this far, but in high school, but if you have three unknowns, you need three equations. Has anybody, I know it's early, but has anybody started registering for courses for next year? Okay, I'm just curious, because if you were, I was going to talk about the whole three equations and three unknowns thing, because it might have a context that you would understand. The other equation is going to be what happens when I put negative 1 in for x, and I get negative 16, and it's worthwhile just to double check everything here, make sure I've got the right function going on in my head, and I do. I put in 2 and get negative 5. I put in negative 1 and I get 16. I'm going to choose, just to organize things for myself and for you, to call these equations equations 1 and 2. And I always, not always, but most of the time, it turns out that you're going to use elimination to eliminate a variable. And what that means is you're going to stack the equations so your A's are lined up and your B's are lined up. And if you add them, you get rid of the A's or you get rid of the B's. So because I'm going to kind of alternate equation 1, 2, and then 1, 2, I just want to number them to keep organized. When I simplify the top equation, I'm going to get 4a right here. I'm going to get 2b. And then, you know, I'm just in teaching mode here. You would want to write this whole line out showing what I'm going to abbreviate with green writing. This is 24. 24. This is negative 9 and negative 5. So I have to take negative 5 and add 9, and that gives me 4. And I have to subtract 24. And I'm going to double check this, but I'm pretty sure it gives me negative 20. And you've just double checked it for me. A couple people, can you? So what I'm interested in is negative 5. I need to add 9. and then I need to subtract the 24. I'm pretty sure it's negative 20. But again, I'm not writing an exam, and if I were, I would be doing it on my calculator to make sure. Even I would be, and I'm pretty good with numbers sometimes. This one, when I square the negative 1, I get 1, positive 1. So I get an A. This is equation 2. I have minus B, and then I have the negative 16, and I'm going to add 9 to that, and I also need to add 3, because negative 1 cubed is negative 1 times the 3 is negative 3. You know, or you could take these two numbers and add them together to get negative 12 and add 12 to negative 16, but I'm pretty confident I get negative 4. And again, this is equation 1 and this is equation 2. It would be nice if this was not 2b, but it was b. And I can arrange that because each of these numbers in the equation are all divisible by 2. I can easily divide both sides of that equation by 2, rewriting equation 1 as 2a. So I'm dividing by 2 is what I'm doing here. 2a plus 1b equals negative 10. And now I have a fighting chance to do this. I'm going to add these equations together and get 3a equals negative 14 because the b's cancel. So a is equal to negative 14 over 3. And every time I go over the questions from this lesson, I always kind of go, is that right? Like normally on an exam, particularly multiple choice or numerical response, the a and the b that you're finding will be nicer numbers. However, I do have the answers here. Yeah, negative 14/3. Now what you have to do, now that you've determined what a is you have to put that back into an equation to find b. And only because I want to avoid a negative, well, no, it doesn't matter. Let's go with this equation. Okay. So I'm going to put a in. I will have negative 14/3 minus b equals negative 4. Jesse, does it make sense to you that since the b is negative, if I move it to the other side, it becomes positive? So I'm going to basically swap these two terms and change their signs. Okay. You know, at some earlier level, you're taught you're adding 4 to both sides, you're adding b to both sides. But what we end up with is b equals 4 minus 14/3, and you can use your calculator at this point or get 12, I think negative 2/3. Okay. So I'm not going to go over 14. 14 is the same deal. And a question like this would be a good written response question. When you write your diploma exam, you will have 3 written response questions. Each of them will have 2 parts, A and B. This would be 1 part of 1 question. Probably this would be a 3-mark question. All right, before we get started today, any other questions from yesterday's work? Go ahead, Lynette. Number 9. Certainly. Let's take a look at number 9. For what value of c, so this is kind of, it has the same flavor as what we just did, but it's not the same question. We have a polynomial and there's a parameter missing, and we're told that when we divide by x minus 2, whatever remainder we get is the same as the remainder we get when we divide by x plus 1. Well, the remainder when we divide by x minus 2 is going to be p of 2, isn't it? And the remainder when we divide by x plus 1 is going to be this, isn't it? But we're told these are equal. So what I can do is put 2 into that expression and get negative 2. My input is in these 3 places. That's where I'm putting this 2. Times 2 cubed plus c times 2 squared minus 5 times 2 plus 2. And now I'm going to put in for the input here, here, and here, negative 1. And when I'm done, I'm going to go back and check from the beginning to make sure I've written everything correctly. I have negative 2 times the input cubed plus c times the input squared minus 5 times the input minus 2. And I'm just going to step back and double check everything, but I'm pretty sure I've entered things correctly on the board. Now it's a matter of simplifying this, and I don't want to use too much time here. 2 cubed is 8 times negative 2 is negative 16. Here I get 4c. Here I get minus 10 plus 2. Again, I'll double check all that in a second. Negative 1 cubed is negative 1 times negative 2 is 2. This is going to be 1c because when I square negative 1, it becomes positive. And then I have plus 5 minus 2. I have a feeling this should be a plus. The reason I knew that is I knew that those 2's on both sides of the equation wouldn't matter because they're both in the same, they're both constant terms. So plus 5 plus 2. I better double check everything now. Negative 16 is correct. 4c is correct. Negative 10, 2. Negative times a negative is positive 2. I get 1c here. I get positive 5 and 2. I'll leave it to you to finish this. You can simplify by crunching all the numbers here and getting 4c minus 24 equals c plus 9, and then you can solve the equation. I don't think this would really rise to the glory of a written response. It would be maybe a numerical response question. Does that help? Okay, we're going to move on now and take a look at the next lesson, which deals with factoring polynomials and what's called the factor theorem. And this is on page 11 of your unit handout. We're going to be factoring polynomials today. So just to take us back in time, if I gave you a linear expression and I said factor it, that's something you learn in grade 9, maybe even grade 8. I'm not as familiar with the junior high curriculum as I should be, but factoring a linear equation is child's play. It's very simple. You would factor a 3 out and have x minus 4. And you do a lot of that in grade 9 and 10. 9 for sure, and definitely 10 you encounter it. And then last year in grade 11, you encounter things like this, where you have a quadratic. It's a higher degree than the one on the left. Notice, by the way, this is a polynomial function. It's polynomial. It's a degree 1 polynomial, which is called linear. But you learn how to factor polynomial functions in grade 9 and 10 as long as they're linear. And then grade 11, well, this is a polynomial. And you learn how to factor this. And there's, many variations to this, but since the coefficient of the x squared is 1, you can just get by with saying what two numbers multiply to give negative 8 and add to give negative 2. So you learn that that's how you factor it. And, if the coefficient, just want to check to make sure that's right. If the coefficient is not 1, then you have some other tools at your disposal. But what I'm telling you is today, at the end of today, you should be able to factor any polynomial, a degree 5 polynomial. And in fact, I think it was just the diploma exam that was just written, one of the written response questions, one of the parts of a written response question, was to factor a degree 5 polynomial function algebraically. So that's what we're learning today. And we're going to use something which is called the factor theorem in order to help us factor polynomials. So if I didn't make the point, because I wrote down a linear, I wrote down a quadratic, the point is that if I just scroll ahead here, we'll come back to this, you should know how to factor something like this by the end of today's class. Okay? And it's not something that you're going to just look at and factor in one step. What it's going to involve is turning it into a cubic, and then turning the cubic into a quadratic, and then going, oh, now I know where to go, because I learned quadratics last year. So let me go back to the beginning here. Warm up. Consider this polynomial. I would like everybody to find the value of the polynomial when x is -1. Now remember what I've told you, and I want you to please follow along to the T what I'm doing on the calculator. I don't want you to do anything different. Okay? I don't want you getting ahead of me. So the quick way to do this, let's say this is a written response, first of all, okay? And you were asked to determine that. You would definitely have to write this, okay? You would. But I hope you could all enter that into your calculator without making a mistake. I really do. Okay? But it's easy to make a mistake. So what I showed you yesterday is, even if this were a written response question, you write that down. No, you don't need to explain to anybody how you got the answer. So what I would personally do is put 3x cubed plus 8x squared plus 3x minus 2. And you're going to see that this will be valuable for later in this same warm-up. And I'm going to double check one time to make sure that I've entered everything correctly. And I'm going to go to my table, and this is where I want to make sure you follow along exactly to the T. Go to table setup, and I want it on ask. I don't want it on auto, please. Later on, you can put it on auto and you can explore some other things, but I need you focused on this method right now. So I go to my table and I enter -1. Now I have some other things in there. So I would say on an exam, you know, this is equal to 0, but I don't need to show how I got that. Are you with me on my kind of keeping something revealed from the marker or hidden from the marker? I'm revealing this, but I'm not telling the marker how I'm finding it. Okay. So what we're saying, and we can, if we like, call this polynomial p of x. What we're saying is p of x when x is -1 is 0. That's what we're saying. We're saying the polynomial has a value of 0 when x is -1. And I'm going to jump right now to the important part of this lesson. Why does that mean x plus 1 is a factor? That is a fact. That's true. Why? I'll give you a hint. It has something very close. Well, it's not very closely related. It's connected to yesterday's lesson, what we learned yesterday. Ariana. Right. P of -1, this is the remainder when you divide by x plus 1. Well, we talked extensively yesterday about the fact that, for example, 3 is a factor of 21 because when you divide 3 into 21, you don't get a remainder. As soon as you divide by something, and we talked about this on the calculator, when you divide numbers, if you don't get decimals, that means there's no remainder, and what you've divided by is a factor. So why is x plus 1 a factor? Well, because p of -1 equals the remainder. And I've kind of already written this over here, but I'm going to formally write it here. When you divide by x plus 1, this is the remainder theorem. Since p of -1 equals 0, the remainder equals 0. Therefore, it's a factor. Therefore, x plus 1 must be a factor. And this is really the factor theorem. 3 dots written like this means, therefore, x plus 1 is a factor. Now, you have to understand something. I led you to this by saying use -1. Right? You don't know what numbers might produce this, but that's going to be part of our problem-solving strategy. All right. Use synthetic division to find the result of dividing the original polynomial by the x plus 1. Okay, this is easy. We put a 3 here, an 8 here, a 3 here, a -2 there. We bring down the 3 to begin with. We put the 0 of the binomial there. We multiply and add, multiply and add. Before I do this, what do we need to get here? What has to be written there in the end? The remainder, which should be 0. That's a nice double check here to make sure that you're on the right track. So I take the -1 times 3, which is -3, and I add that, and I get 5. I take -1 times 5 and get -5, and I add that and get -2. I take -1 times -2 and I add that and I get 2. And all is right in the world because I get 0. Now, think about this for a second. We've divided a polynomial by something that we know is a factor, and we've got, as a result, that. Well, if you take 21 and divide by 3, you get 7, right? That tells you that 7 times 3 is 21. That tells us that this original polynomial now, this thing, is equal to the x plus 1 times the 3x squared plus 5x minus 2. And question D says, write the polynomial in factored form, but we have whittled away this degree 3 polynomial into a linear factor and a quadratic factor. You ought to be able to factor the quadratic one. I'm a trial and error kind of guy. I will tell you right now, I don't know if we had this discussion. Do you remember a teacher in grade 10 teaching you something called the method of decomposition? I'm not asking if you've learned it. I'm not asking if you remember how to do it. Do you remember your teacher teaching it to you? Well, a lot of students don't even remember it being taught to them. I rarely come across a student who remembers the method of decomposition. There may be the odd person in the room who wants to use it, but at this level, we don't have time for it. We use trial and error. These two terms have to multiply to give 3x squared, which means the only options are 3x and x. These two terms have to multiply to give -2. So when I do trial and error, I don't worry about the negative. I just go, well, it's got to be 2 and 1. And I try putting the 2 in one place and the 1 in the other. And it's hard for me not to figure out which way to put it. So I'm just going to go with 2, 1 in the order I said. I'm going to try the 2 here and the 1 here. And then what you would do is you would say that when I FOIL this out, this is just scrap paperwork almost, I would get 3x squared. And that's good because I want 3x squared. I would get for my outer 2, or sorry, for my last 2, and that's good. If you're really on top of your game, you'll understand I don't need to check those. I put those things there so I would get 3x squared and 2. I'm really interested in this, which is 2x, and my outer, which is 3x, and I'm asking myself, well, this is good. I'm glad this happened. Can I combine those to get 5x? And all of you are nodding your head, but the answer is no, I can't. Because this has to be negative. One of these numbers, the 2 or the 1, is negative and one is positive. So it's either this, which would not give me 5x, or this, which would not give me 5x. Okay, well, what do you do then? It's called trial and error for a reason. Try this. And now you'll see that the outer is 6x, and if the outer is positive 6x and the inner is negative 1x, they combine to give the 5x. So that's it in factored form. And, you know, it's just a fact that you have to be able to factor quadratics relatively quickly. It shouldn't be something that you stare at this quadratic expression for 5 minutes or you work on it for 5 minutes. It should be kind of under a minute. All right. Notice that, and we've already talked about this, since the remainder of the division was 0, the divisor must have been a factor of the polynomial. It's the most important point about today's lesson. Can you apply what you already know about the remainder in division of things to express a polynomial in factored? Does your handout say factored for or factored form? It says for? Okay. All right, let's turn the page. This is the factor theorem. If x minus a is a factor of the polynomial, then p of a equals 0. What we do when we factor, though, is we turn that around and we say, if p of a equals 0, then x minus a is a factor. And I'm talking about it this way because when you factor, you don't know the factors. You want to find the factors. Well, how do you find the factors? You find values of x that make the polynomial 0. And again, please try not to get ahead of me on this. If we can identify a number for x that will make a polynomial 0, then we will have identified a corresponding factor. If I put the number 2 into a polynomial and I get 0, I know x minus 2 is a factor. If I put the number 2 into a different polynomial and I get 12, well, I know x minus 2 is not a factor. The question becomes then, what numbers do you try? Like, are you just throwing darts at a board and trying, oh, I'll try 13? Clearly not. We're going to go back to what we learned day before yesterday and kind of talked about it a little bit yesterday, but mostly day before yesterday's class. And this is now formally in your notes. If x minus a is a factor, a must be a factor of the constant term. Let me break that down for you. There are two ways we write polynomial functions. One of them is the way that I have at the top of the screen, which we would call factored form. And if you were to multiply all that out, which would be crazy talk, I don't think we want to go down that road. But if you were to multiply that out, you get what's called the expanded form. We learned that if you multiply out those 4 terms that I've highlighted, you will get the first term of the expanded form. We've learned that if you multiply out the constant term in each factor, you'll get the constant term. And then we've learned that you get some other things there, right? But I want you to notice that these 2 factors that I've highlighted are x minus a factors, aren't they? The other factors are not. The other factors are not x minus a. Their zeros are more complicated. The 0 of this factor is not -3. It's -3 divided by 2. The 0 of this factor is -5 divided by 3. They're more complicated. We're talking about factors that look like x minus a. Well, what is the value of a in each of these? A is 2 there, right? A is 1 there. I hope everybody sees why the number 30 has to be containing 2 as a factor, because you got 30 by multiplying 2 by some other things. So what are values of x that we try to make the polynomial 0? We try numbers that are factors of the constant term. Let's do this. X cubed minus 7x minus 6. Okay, so what you would do on a written response is you would say potential zeros would be x equals positive 2, negative 2, positive 3, negative 3, positive 6, negative 6, positive 1, negative 1. I'm listing all of the factors of the constant term, which is negative 6. I hope it's obvious. I will say, just in case it isn't, you probably want to start with 1. You probably want to start with the simplest numbers. And rather than, so we're doing a written response, okay? But I'm going to walk away from my exam paper right now, and I'm going to go to my graphing calculator, and I'm going to put this in for y1. I'm not going to say I used my graphing calculator. Don't do that, because it's a written response. You're kind of cheating the system here. Put in x cubed minus 7x minus 6. Double check it. Make sure it's right. Go to your table. Oh, there we go. Now I lucked out. I had negative 1 in there from the last question, didn't I? So what you would do then, if this were a written response, is you would say, you'd write that. You're not going to explain, I mean, you could say I tried different numbers on my calculator, but I wouldn't go down that road. I would just say, look, I know, and I'm showing you that p of negative 1 is 0, therefore, x minus negative 1, which is x plus 1, is a factor. So how do you factor that x plus 1 out? You do synthetic division. Right? We're going to take x cubed. Help me out here. Is it minus 7x minus 6? X cubed minus, well, just a second here. There's no x squared, is there? We have to put a 0 for the x squared, and then a negative 7 for the x, and then a negative 6 for the constant term. And we put the number negative 1 here and bring the first number down. And this should be 0. If it isn't, you've made a mistake in your synthetic division, or you've made a mistake in saying p of negative 1 is 0. Maybe you made a mistake there. Maybe you entered the thing wrong in your calculator. So I multiply. Negative 1 times 1 is negative 1. I add, I get negative 1. I multiply, I get 1. I add, I get negative 6. I multiply, I get 6. All is right in the world. I get nothing. Which means we're asked to factor this. And I'm presenting this as if it were a written response question. So from here, you would say that means x cubed minus 7x minus 6 is equal to the x plus 1 multiplied by x squared minus x minus 6. And then you can factor that quadratic and you're done. So in factored form, it's x plus 1. And we're looking for two numbers that multiply to give negative 6 and add to give negative 1. I believe they're negative 3 and 2. So we're done. So you've just learned how to factor a degree 3 polynomial. Any questions with that first example? Right. Another degree 3. So what are potential zeros? And listen very carefully. I'm not going to write down everything like it's a written response this time. Okay? It's just you and me. We're just working on this together. We're going to try x equals plus or minus 1 and plus or minus 5. Clearly, you're going to try 1 first. So we don't need to do it this way, but do you see, since if 1 doesn't work and negative 1 doesn't work, then we have to try other numbers, and this is the most efficient way of trying a whole bunch of different numbers? I hope you see that. 2x cubed, and again, this is just how I enter them, plus 9x squared minus 6x minus 5. Just do a thorough double check before you leave this screen. Okay, well, my negative 1 is still hanging out from last time. It doesn't give me 0. What about 1? 1 does. So, on a written response, you would show that P of 1 is equal to 0. But what we've discovered here is what I'm writing is less detailed than if it were a written response. P of 1 is 0, so x minus 1 is a factor. Again, this is the third or fourth time I've said it. This is not what you would put for written. This is just you and I working on math, learning and teaching. So now I can take 2x cubed plus 9x squared minus 6x minus 5 and divide it by x minus 1, which has a 0 or an a value of positive 1. Bring the 2 down. I'm off and running. 1 times 2 is 2. Add, you get 11. Now, it's at this point where I get a little nervous. Like as a teacher, I go, 11? Oh, man. Because I know it has to reduce to 0, and 11 is all of a sudden a big number. So I'm a little leery about this, but what happens when I multiply again and add? Now things start to settle down. And I see that it's going to work because 1 times 5 is negative 5. 1 times 5 is 5. And I add to give 0. So this means 2x squared plus 11x plus 5. Remainder of 0, of course. And that means that both the x minus 1 and the 2x squared plus 11x plus 5 are factors. So P of x, the original polynomial, is the product of that. By the way, just because this is a degree 3 polynomial doesn't mean it's always going to factor into 3 factors. Maybe this quadratic is not factorable, but I believe it is. Can you do the b squared minus 4ac test? Well, you get 81, don't you? 81 is a perfect square. That means it's factorable. That means I can not waste my time, but use my time to factor it. If it were 71, I would be wasting my time because it's not factorable. So my polynomial factors, I'm going to do trial and error. Well, it's got to be 2x and x. No. When we say things are factorable, we mean with whole numbers. The only 2 numbers that are whole numbers or integers that multiply to give the 2 would be 2 and 1. That's a bit of a lie because I guess the integers negative 1 and negative 2 would do it, but man, you'd never factor it with negatives out in front. 5 and 1, how many of you see that if by putting the 5 here, I'm going to be getting close to 11x when I start multiplying it out? And this is what I mean by being able to factor things relatively quickly. It really helps to know your times tables, your math facts, but that's it in factored form. By the way, sooner or later, somebody would wonder, what if instead of trying 1, you tried negative 5 first, and you discovered it's a 0? Well, then you would do synthetic division with that, and what you would discover when you divided by x plus 5 is you would get a quotient of 2x squared minus x minus 1. And that factors into the other two factors. So it doesn't matter the order in which you extract the factors. You're going to end up in the same place. So degree 4. And this is the last example in this set, right? And then there's one more question. Okay. So what are we going to check for potential zeros? You're going to check x equals plus or minus 1, plus or minus 2. And these are going to be factors of 24. I would suggest to you that if you haven't found one by the time you've checked all 4 of these, you probably made a mistake somewhere. You're not going to typically have a question where all of the factors are like x minus 8 and x minus 12 and those numbers. There's usually a 1 or a 2 involved. But I'll write down the potential zeros just to be clear. Man, there are a boatload of numbers that are factors of 24. And as I said, man, if you're going to try these, don't start with the 24 and work your way down, right? Did I get them all, or are there other numbers? I think that's it. 6 and 4, 8 and 3, 2 and 12, 1 and 24. Again, just cheating the system a little bit here. 5, 1, 2, 3, 4, minus 13 cubed minus 14x squared plus 52x minus 24. Just do, as I said, a thorough double check. I think that looks okay. Go to my table. 1. I always start with 1. Nope, negative 1. No, 2. 2. Okay. So P of 2 equals 0. That tells us x minus 2 is a factor. So we are going to have to perform now synthetic division of that polynomial. I'm just putting this here so I don't have to scroll back up. Of that polynomial by x minus 2. So we have 5x to the 4 minus 13x cubed minus 14x squared plus 52x minus 24. I'm going to divide by x minus 2, which means a 2 goes there, and the 5 falls below the line. And again, my hope, no, not my hope, confidence tells me I'm going to get 0 there. I'm going to double check to make sure I've written everything down, but if I didn't get 0, then I would really for sure double check. 5, negative 13, negative 14, 52, and negative 24. 10, add, negative 6, add, negative 20, add, 24. All right, all is fine. I'm happy with that. Now, what that means, everybody, and I'm actually going to write this down on the whiteboard because I don't want to interrupt the flow of what we're doing. What that means is our original polynomial is equal to x minus 2 multiplied by 5x cubed minus 3x squared minus 20x plus 12. Okay? And now what we need to do is find a factor of this. And for a reason that I don't want to explain just yet in detail, if we can find a factor of that, it will also be a factor of the original polynomial. But at this point, I don't want you using the original polynomial. I want you entering this to find a factor of it. I guess I will just briefly explain the reason why. It could be that x minus 2 is a factor again. If x minus 2 is a factor twice, you're not going to know it by looking here. I don't know that it is or not. I think it might be, but we'll see. So now I'm going to put in 5x cubed minus 3x squared minus 20x plus 12. By the way, I hope it's clear that why I'm doing this again. This is cubic. I still can't factor it on my own. I need to take out another factor to make it quadratic. 5, negative 3, negative 20, 12. I go to my table. Okay, 2 is a 0 of this as well. And you wouldn't have noticed that if you kept the original function in there, because we've already seen 2 gives you 0. But 2 gives you 0 again. And that means that there's another factor of x plus 2. So in this, f of 2 is also equal to 0, which means x minus 2 is a factor. And now we're going to do synthetic division here. And this is why I didn't want to write a bunch of stuff, because I think it's an efficient use of your time here to just do this. I mean, you could rewrite all those numbers, but we just keep dividing and dividing and dividing. So I multiply the 2 times the 5, which gives 10, and I add it to negative 3. 2 times 7 is 14. I add it to negative 20. 2 times negative 6 is negative 12. And I get 0. That's what I want. So now going back to what I've written on the whiteboard, what does this tell us? It tells us the original polynomial had a factor of x minus 2, and then the other factor was the 5x cubed minus 3x squared minus 20x plus 20, but that has a factor of x minus 2 and a factor of 5x squared plus 7x minus 6. And that, I view it this way. We've chipped it down to a quadratic. We've whittled it down until we see there's a quadratic, which nobody should have difficulty factoring at this level. You could do your b squared minus 4ac test, but I'm pretty sure it's factorable. 3 and 2, I want 7. See, just let me verbalize what's going on in my head right now. I'm thinking 3 and 2 for the 6, and I immediately thought, what if I put a 3 here? And if I put a 3 there, I'm getting 15x for the outer, and I don't know how I'm going to change that to a 7. 15 is a pretty big number. So I suspect that it's a 3 here and a 2 here. I guess if that's positive and that's negative, it's factored correctly. As I said on the last written response there's 3 written response on the last diploma exam. 3 written responses what you have. Each of them has 2 parts. One of the parts of one of the written response was a degree 5 polynomial to factor. So you need to be on top of your game. Before we do the final example, 2 things. Any questions with any of the work here? Okay. What if you had a polynomial that you were asked to factor, and it turned out that in factored form it was this? Are you with me? The answer is you would never be given something that factors into that, because you would only be able to extract with the factor theorem the x minus 3, and you would be left with a cubic that has no x minus a factors, and you can't factor that. You'd have to use a different theorem. So you would never see that. What that tells you, and I hope this makes sense, I could have explained it a little better, is you will only ever be expected to factor things that have at most two of these oddball factors. And very often that's the case. You have a whole bunch of x minus a's, and then you have two that are not x minus a's. But you should be able to take out every x minus a to be left with a quadratic. This is fair game. That's fair game. That's not. Right? So at most, two of these non-x minus a factors. Let's take a look at one final question, and this is a very basic question. In fact, it's really, I hope everybody sees the factor theorem is just a specific case of the remainder theorem. The remainder theorem says when you divide a polynomial by x minus 4, the remainder should equal p of 4, correct? That's what the remainder theorem says. But if you're told x minus 4 is a factor, then the remainder is 0. So what we did at the beginning of class with question 15, where we said we put in a and we write the remainder, we're doing here, but we're just writing 0. 0 has to equal p of 4. So 2 times 4 to the 4 plus k times 4 cubed plus 19 times 4 squared plus 20 times 4 minus 24, and I ran out of room, so I'll put it on the other side, has to equal 0. It has to equal the remainder. And as I said, the factor theorem, which says p of 4 is going to give you 0, is just a special case of the remainder theorem. Because if it's a factor, the remainder is 0. We got a lot of numbers to crunch here. I'm going to want some help here from you with your calculators. I believe this is 512. This is 64k. This is 80. And this is 24. Is this 304? Okay. Getting to that age where my memory slips from time to time and I just like to practice them. Yep. Oh, thank you very much. So it's not 80. 10x. This is 40. Good catch. It is 512, 64, 304. Okay, so we can just combine all these numbers together. We're going to get 64k plus 512, 816, 856, 832, plus 832 equals 0. So we have to subtract 832 from both sides and then divide by 64. And the left side of my brain just took a look at the right side of my brain and said, let's take a nap. I don't want to do that, okay? Could you tell me what you get? Negative 13? I was going to say that. I wasn't, actually. Negative 13. So the value of that missing parameter is negative 13. The strategy you use is the same thing. You have to put in a pair of numbers that make the equation true. And in this case, we put in 4 for x, and we set the whole thing equal to the remainder, which was 0. Some practice problems, you know the drill. Textbook questions are good to practice, especially, I suspect that when you take a look at 15, it's like what we did before with the 15 from today. And then I have some multiple choice and numerical response questions as well. And I think you have about 20 minutes here to work on this. Okay.